Here we go. Okay, the record is on. So let us try to come back here. Now, you know that the reason that I make the moment equation for the actual case is slightly more complicated than it has to be is because I want to use the easier one on the virtual load case. Just my style, you don't have to do it, okay? So now the virtual, okay? Generally, yeah, I would squeeze this in. So let me try to do the same. So I'm just going to remove this. No, not remove this. Move this more out of the way so that I can write my virtual equation. Okay. Technicolor would help. So now that would be my virtual moment. Okay. And I should try to write this somewhere. It's the same beam. No, let's not do it here. Virtual load. It's the same beam, you know, basically. And now we apply the virtual load at the location that we want to know. The deflection, it would be that one, okay? And right. So that's the virtual load, star or not. And now I need to use the same range. Okay, so my X would begin from the tip of the beam. And that would mean now my moment equation for the virtual load case from 0 to 5 meters would be minus X. It's exactly similar kind of load to this 10 tons, but it's 1 instead. But take a look at the next equation. Because it's 5 to 10, and when I am here, actually the moment equation does not change because my range here is continuous. So the moment equation for the virtual load case remains minus X. I love to have this kind of luxury because it would help even more when we are dealing with this in the solving the indeterminate structure. Okay, it will be even more beneficial in the future if you write it like this. So that's what I have now. Okay, so I don't have anything else to do but just to move forward. But I can squeeze in another case where, let's change color. If I want to know the rotation at C, it's the same beam now. But this time I will apply the unit moment instead. And look at this. If I'm going to write my moment equation and it's unit moment, so that means my moment equation becomes just a constant, right? Of minus 1. So this is for the calculation of delta C. Meanwhile, this is for the calculation of delta C. Okay, now it's time to sum up the work. Remember that this is the work of the entire system, so you must include everything. So let's say for delta C, actually I could use the capital delta, it's better. diversity. This is going to be equal to the first is EI. Okay, so first part, the first integral is 1 over EI. Integral from 0 to 5. The actual load case is minus 10x. The virtual load case is minus x dx. The second is plus, right? The second has 2 EI. And the integral from 5 to 10. It doesn't look much like 5. Let me fix it. Okay, and say the actual moment is now minus 10x minus 2.5 x minus 5 square over 2. And then look like 2 again. That's the actual moment. And then the virtual one is also minus x dx. Okay. You know, you should be able to notice that up to this point, you require proper engineering knowledge so that you could write the moment equation. You also need small mathematical knowledge to know that you need to write the equations in the same domain so that you can multiply them together. After this, it's pure mathematical work now. So I tend to give a lot of percentage up until this point. I don't remember, but we can look. That's 2 to 3. 1. OBE description here. Now we are dealing with virtual work. If we are going to calculate the virtual work alone on truss on frame, you see here. If you can construct the proper moment equation with the correct range and stuff, you already got 80%. So I underline the importance of using the engineering knowledge to come up with a proper expression for integrals. If you can carry out the integral, it's 20% more on top. So if you are not excellent in handling mathematics, you know, up until this and everything is correct, for virtual work, this is already 80%. If you get the result correctly, that's 20% more. And I think it's fair enough because, say, you should be able to write the moment equation from your days of statics, right? And folks, you could also use your calculator to carry out this dirty work for you. Your calculator can do it, I know, because I got one just like yours. So I'm not gonna go. I'm not gonna go in through details now because it's a lot of numbers. Actually, you know, in my hand now, I did it by my hand. So anyway, this is about 2102 with some decimals over EI. One more thing that you should know is the sign of your result. This is positive. What does it mean? What does the positive work mean? Anyone care to try?
The deflection is upward.
Is what? Say again, please. The deflection is
Upward.
thank you for trying, but no. Okay. More, please.
The deflection go down.
This is not wrong, but it's not the say accurate answer either. Nathawarit นะครับ you can't have the upward deflection at all because you see the load. You have all kinds of downward external loads, right? So you would expect your beam to go down at C. Okay. And yes, Akarapan, this is the downward deflection, but that's not the meaning of the positive result here for the virtual work. Anyone else? Thank you for your efforts. Nah? Thanks a lot. Anyone else?
It's going the same direction as the virtual load.
Yes, is the correct answer. Thank you, Nakarin. A round of applause. This is work. When you have positive work, it means that the work is in the same direction as the unit load. Remember that the result here, if you go back to the class note, see, that's the work. The work of your unit load. So if your work is positive, it means everything goes in the same direction. So when you apply the downward load and your work comes out to be positive, it means that positive mean deflection or deformation is in the same direction, that's my direction, okay, as your unit load. Okay, that is the most important thing. You wouldn't be surprised, right? Because you guys have learned about work since high school, right? You know what I think I'm thinking about, because I have written a lot of things on this good note. Maybe in the end I should also post what I have written on good note on Facebook as well. Don't you think so? Just to help you a little more. Okay. Okay, so that's that. So now let's try to finish our job on delta C. So it's going similarly. We have the first portion, the integral 1 over EI. The range is from 0 to 5. The actual load remains the same, right? Minus 10x. The virtual load this time, it's the work of this moment. So it becomes this instead, minus 1. And then for the second person, it has 2EI. Integral will be from 5 to 10. And the moment equation is going to be this one. Now I'm kind of lazy, so let me use the technology. Now you know it's the same thing as well. Okay, but this time multiply by, oops, sorry, minus 1 dx. Oops, forget the dx here. Okay, and play some calculation music with your calculator. In the end, you would have the answer equal to 338.5 over EI. Again, this is positive, means you guys cannot fill in the blank yourselves, right? And this is another one that you should practice, right? And I'm just going to say in the video that mean, this is a verb. So when you say it means, it's kind of difficult if you don't practice. So some of you would say it's mean. If you say it's mean, this means cruel. It's cruel. It means, okay, practice it. Not that difficult, not the most difficult thing in the world. Okay, not it's mean. No, it means. Just if you can't pronounce it, say it slowly. People tend to bury their error or mistakes or shortcomings by trying to speak fast, but that only makes it worse. Speak slowly. Okay? Begin from doing it slow, just like when you play music, you know. When you practice music, you begin by doing it slowly, because if you cannot do it slowly, you cannot do it fast. It's a fact. So it means, and to speak one word at a time, it means, not it's mean. Why in a rush? Do you have a plane to catch somewhere or something? Right? Okay, so that's it. Any question for this problem? Okay, so no question. So let's move forward. Wow, because because of the online thing, we can actually go very fast. And one good thing about this is that I can include so many examples, much more so than the on-site classes, you know. So if you are diligent enough and if you really want to find, you should try and go back and watch all these videos, because you know when I choose the examples, I don't choose them just because they look beautiful. I choose them on purpose because each and every one of them can show you something that you may find useful in the future. For example, this problem, it would show you how you can manage the range of the say the problem. Okay, let's say I may have gone too quickly with the problem with this one. I did not show you much of the free body diagram, but I hope this is fine. And you can also alternatively use a different range. For me, you can write the moment equations by using the range from 0 to 5 as well. And since you don't ask me anything, let me show it for you. Alternatively, what's that? Okay, let's say if how do I write this? Let's use the same fashion. Okay, all right. You guys can see the picture of the beam somewhere, right? I can't move up that far. Portion BC, our big M is going to be the minus 10x But for member and range here, let's put it down here. 0 to 5. But instead of using a range from 5 to 10, I can also write the moment equation from 0 to 5. But if you are going to begin your x from 0 to 5, you have to be very, very mindful of what's going to happen, because your free body diagram that starts from here. If you want to start your x from this 5 location, you must be aware that, you know, at this location there is moment from the effect of this 10 tons load, right? And that is already minus 50. So if you want to use this range, that means you must have this minus 50 and then minus, what's the W? 2.5 x squared over 2. Remember, it's pretty similar if I go back here and substitute 5 into my moment equation. If I substitute 5 here, this term becomes 0 and I have minus 50, which is the beginning value for your moment equation here. Because when I substitute 0 here into my moment equation, I get minus 50. So it's the same, you see, but the range is different. All right. And now things will get slightly more difficult because if I do this, my virtual work case will have to be split as well. And some of you will forget. This is 1, so this is minus 5. And that is also minus 5. So I'll do it again. I can move the range out. And now I can write the virtual moment for this. That the first one is going to be minus x. But the second one, because you now use this range, so your x will begin from here. And when you look at the free body diagram, you now have minus 5 a moment and then another load, right? Because that's a complete free body diagram. Let me complete it, okay? That's that. And actually, there is also 10 here as well, right? So I missed that. You need to have minus 10x here as well, right? See that? So I forgot this because I did not complete my free body diagram in the beginning. So you have the extra shear here as well, and the moment, and then the uniform load. So that comes with a price. And so this, let's come back to the virtual work case. Now I have minus x minus 5. See, the key is always to complete your free body diagram. And then for the moment case, because the moment is constant, so this one, you know, even you are not aware of this, it's just going to be the same. So minus 1 and minus 1. Okay, is there any question? Are we crystal clear? I hope so. Okay. I'm glad that I covered that. So let's face this now. Find slope at B and C and deflection at A and B. So where are they? Take a look. Okay. Hang on. Seems to me that they should be pretty straightforward. So yeah, A, B, C, and D. Now what do we want? We want slope at B and C, or the rotation here and here. And we also want the displacement at A and D. So it seems to be like a lot of work, right? So let's start it, okay? I am not going to go through the calculation of the reaction. All right, let me go ahead and give you the reactions right away. That's 4. That's 3.5. So we need 3 ranges, apparently. The first range for portion AB, the second for BC, and the third is for CD. So now the trick is that when you write for AB, let's see if I can squeeze everything in one line. Let's try. Portion AB. If you choose to do it from A to B, you must do so for all the load cases. Okay, so let's say my big M would be minus X, minus 1X, right? And for BC, if I choose to write my moment from B, maybe the better. If I choose to write it from B, I need to do so for everything, but I think I choose to write it from B because when we calculate the slope or rotation at B and C, I can apply the unit moment there. So it's very easy in those cases to begin from B. So that's why I began from B. You know, I look thoroughly at the problem. But when we began from B, this one ton, because it's also a point load, it becomes a constant moment instead. Right, so that's pretty convenient. Because when you write the moment BC, this portion, in fact, can be replaced by constant moment of 1 multiplied by 1.5. So it's 1.5 like that. Apply at the end of the beam like that. And I can do so with this CD, right? I can replace this portion by this 1.5 as well. Can I do that, folks? Of course I can, right? So the moment equation at BC would be minus 1.5. It's a constant moment now. And because the reaction accounts for this point load, right? Unlike the previous case, I can easily say plus 4x. Oh. No, it's not. So the reaction here, we need another free body diagram. Sorry, my apologies. It's not going anywhere. So we have this 1 and then reaction at 4. So the free body diagram at the beginning of this portion, the shear is down to just 3. Right? And then minus W, which is 1, x squared over 2. Okay, let me write the free body diagram again so that you see what's going on. Right here at the support, I already eliminated the overhanging portion, so I now have the shear of 1 and then the moment of 1.5, correct? Because the free body diagram on the left would be this this, and then that. Right, guys? So now let's come back here. We have the reaction equal to 4. So if I cut the free body diagram slightly beyond the support itself, what I would have would be this, because this is 4, so I have 3. And then I have the same moment. Right? That's why we got 3 here. And I have a hunch that this may be useful again in the future. Oops. So let's keep it for now. Okay. So that becomes the moment equation for BC. And for CD, again, it's easier to write from right to left, from D to C, and our equation becomes minus 0.5x. Okay, so that is for the actual. So now let's move on to the calculation of the for the calculation of deflection at A. Now I need to apply the, let's use some strange color. Too strange would be nice. It wouldn't be nice. Okay, so let's use this one. To calculate the vertical deflection at A, you now need to apply the unit load at A. This is when things can become hairy, and you must be aware of the direction of the force. I am applying the downward unit load here. So in the end, if I get the positive work, it means that my deflection is also downward, just like the unit load. Okay. And when I apply this, the reaction here is 5/4, and here is downward 1/4. And again, I can replace this portion with this. Okay, so then I can have something similar. 5/4, 1, and then a moment of 1 multiplied by 1.5. So my moment is 1.5 here. All right. So again, this will cancel each other out, leaving you with a 1/4 upward force. So your moment equation here for AB, it's the same. So it's minus x. But this is a constant moment of minus 1.5 plus x over 4. But then for CD, you see, because this system, it has no load on this portion, so we might as well remove this. Right? 0 force. So doesn't affect our structure, and this becomes 0. So that's the second case. Now we move on to the third case. That is the rotation at B. When I want to know the rotation at B, I apply the unit moment. And my unit moment is there. I need a couple, right? If moment is 1, you need a couple of the reaction to help resist this. So it's going to be another couple, but they are 6 meters apart. So you can see this is 1/6 right away. Easy, right? And you can see again that, there's no load on this portion, neither on this. So basically we have like a simple beam for the second case. And therefore this becomes 0 and 0. And be careful, because before this we use the x that begin from B. So this has to begin from B as well. And this is my unit moment. And it's going up, so it's positive. So it becomes 1 minus x over 6. Right? And let's move them over. Lasso, very useful. Oh, okay. It wouldn't go beyond that. I cannot, you know what? One moment. I can actually cut it, right? Yeah. And paste it here. Okay, let's keep them for now. Now, because I want you to see more clearly, it's rotation at C. So we are doing the same. But now you know that if I apply the unit moment at C, the cantilever proportion no longer affects our calculation at all. So I might as well write only this. And then I have the unit moment here, okay? And this time it's clockwise here. And so I need a couple of 1/6 in this direction instead. So because we write the moment equation from this, so that we are consistent and we can multiply our function, this becomes minus x over 6. Also be consistent with the direction of the moment for every case, okay? If you're using the upward or clockwise as a positive, it must always be so for every load condition. You don't juggle this around the sign convention, because otherwise in the end it will be a mess. So that's it. Now we come down to the last case. Okay, let's use this one. Okay, now the last case. It's a unit load here. Okay, and you should see that this again, this portion doesn't matter. Okay, and now when we do this, this is 1.5 up, and then this is a downward force of 0.5. And again, be mindful that you need to write the moment equation from here and from there. Here is 0. There is minus 0.5 multiplied by x. And here it becomes minus x. Right? Is there any question? Oh, the chat. Y minus You mean the pink one?
For the picture in the left teacher, but
This
down
one?
in yes, but down in 1/6, right? But in the live is minus 1.6.
In the right?
Yes, you can see the picture. This I want to wait a
Yes, of
minute.
course. This is a
This-
force, right? But we need a moment, so it becomes minus.
Yes, but this
Yeah,
for why
thanks,
minus?
thanks. So yeah, in fact, I don't need to write minus. I think it's just like an automatic kind of thing.
Oh,
It's 1/6.
okay.
Okay, thanks. It's like the residual thing. Okay, so that's that. So now, again, our hard work is almost over. When you got into this point, you use your engineering knowledge to write the proper moment equation based on a little knowledge about the domain. You need to have the same domain for your function so that you can multiply them. And the way you write the equation, you must always use the same origin and the same sign convention. So now it's just, multiplying them. And I don't have the range, but it should be okay, right? We try to squeeze it in here, maybe. Range. First one is, of course, from 0 to 1.5. The second one is from 0 to 6. The last one, 0 to 3. So we can easily finish this. Okay, the first one, delta A, that's 3 integrals. Let's take 1 over EI out of the thing first. This is going to be huge integral. The first one, if you can manage to see all the equations that I already put there, okay? The range is 0 to 1.5. The actual moment is minus x. The virtual is also minus x dx. Second one, remember, let me scroll up a little bit. Now you want the deflection at A, so it's this first two, right? We are dealing with the first two. Okay. The second one is minus 1.5 plus 3x minus x squared over 2. So this has to be coupled with the this one. See that 2 together. So it's minus 1.5 plus x over 4 dx. Oops, forgot the integral, right? 0 to 6. And that's it. Because the third term is 0. Okay. Now, is that a question? Let's move on to the second one now. That's delta C. So again, it's 1 over EI. And we have so many 0 terms, I suppose. So in the end, it's only the middle term that is left from 0 to 6. Am I correct? Yeah, right. So because for the zeta C, it's now this. And that, right? So it's only the middle term. So again, I can do this. Group. That is. Oh, got that along as well. So, all right. It's 1 minus x over 6. dx. Okay. The third term, delta d now, this is going to be again 1 over ei. For delta d, we also have everything almost in 0. Okay, for delta d, it's now this couple. All right. So yeah, it's almost pretty similar to this. I only need to change the second term, so I'm just going to copy this. Oh, I can also recolor. I didn't know that. But in this term, I need to change this into that. So the 1 is gone. Okay, so that's the zeta d. And the last one is delta d. The last one, we have now 2 terms. So I better write them. It's 1 over ei. And yeah, because this one is long, but anyway, 0 to 6 minus 1.5 plus 3x minus x squared over 2, and then multiply by the minus x over 2, right? It's a bracket here. Then from 0 to 3 this time. And the equation would be, what is it? Okay, the last one is now this. So it's that one, okay? A half minus x over 2. Oh, no, minus x instead. Minus x over 2, that's correct. But then this becomes minus x. Okay, dx. That's my x. Okay, all right. So then that's it, ladies and gentlemen. After quite some time to finish the work, and you can of course play your calculation music. The first one is equal to minus 5.625 over ei. Now it's the negative value. What does it mean, folks? You go back to this. See the blue one? We apply the downward unit force here, but we got the negative work. So that means the direction is opposite to the direction of the load we apply, right? And this is kind of fun because when you have a structure like a cantilever beam like this, that means the load is so heavy that this portion A is in fact going upward, right? It is possible because if the load in the middle of the beam here is so big, it would push the beam down so that, you know, the end can go up like that. So that means you would expect the zeta b to be positive value as well. Otherwise, you can't have something like that. Does it appear to be so? Wow, my handwriting is quite a mess. I think, yeah, in the end is 4.5 over EI. Zeta D is minus 4.5 over EI. So again, zeta D is you know, because we apply the clockwise unit moment there. All right. This is what we apply. The clockwise unit moment, but we got the negative value. So it means that our rotation at C is in fact going in this direction. See, just like the deflected shape. Okay. And the last one, we have minus 9 over EI. Again, negative value. You should write the footnote yourself that negative, what's the meaning of negative values? Okay. Negative values mean, now it's a plural, right? So I don't have to means. I'd say negative values mean, you just fill in the blank, okay? And of course, we apply the downward unit load here, but the value is negative. It means that this portion is also go up like that because the load in the middle is so heavy. Okay. Right, we come to the end of the second session as well. So is there any question?
Teacher, can you go down?
Yes, I can. I mean, you mean move down, right? If I
Move down ค่ะ
go down under the table. Okay, yeah.
Okay ค่ะ
Okay. All right, folks. More questions, maybe? Okay, let me stop the record.